All right, welcome to the second video of our last week together. This is 12.5 and it's going to focus on the volume of pyramids and cones. So just two formulas we're going to focus on. So the first one is the volume of a pyramid is equal to 1/3 of the product of the height and the area of the base. So I'm just going to show you two examples of where that comes from. Okay, so I've already split a little bit, so this might not work out perfectly, but you'll get the gist. So I want to show you why the formula for a pyramid is 1/3 the base times the height. So you just learned in the previous videos that for a prism, the formula is just base area times height. That's what I have right here as a prism. Then on my other hand, I have a pyramid. Now, the square base of the prism and the pyramid are the exact same, and they also have the same height, these two figures. So far I've taken two of these pyramids, filled them with water, and filled up my prism. So now if I take this final pyramid and pour it in, and I'm spilling it all over myself, you'll notice that now this one is filled up. So it took three of these pyramids in order to fill up the one prism. So that's why the formula is 1/3 base times height, because the area of the pyramid is 1/3 of the prism. So here's one other way to visualize the volume of a pyramid. So I've got my three very poorly made pyramids right here. And this is actually what I would have shown you if we were in school. So if I take these three pyramids, because the formula is 1/3 of a regular prism, if I take these three, I can actually form a rectangular prism. So if I put these two together, and there's a good GeoGebra of this too. So if I put these two together and I take the third one, you'll see I've actually just created a cube. So that's also why the volume of a pyramid is 1/3 that of the volume of a rectangular prism, because three of them make one prism. Okay, so now that we've talked about pyramids, let's talk about cones. The volume of a cone is very similar. It is 1/3 the product of the height and the area of the base, or in this case, 1/3 pi r squared h, because the base will always be a circle. So let me show you where that comes from. Okay, so very similar to the last experiment. So right here I have a cylinder. Now I'm already spilling the water all over myself, so hopefully this works out. But I have a cylinder with a circular base, and then I have a cone with the same circular base. So the two circular bases have the same area. These two also have the same height. So far I've put one cone inside my cylinder. And you can kind of see it's starting to look like it's probably about 1/3 of the way full. So I'm going to put in two more of these. So there's one. Okay, and here's the final third one. And again, I spilled a lot of water, so hopefully it matches up enough. I'm already spilling water on the floor. So you'll see I filled up the cylinder. So it took three of these cones in order to fill up the cylinder. So that's why the formula, similar to the pyramid, is 1/3 pi r squared h, because the formula of a cylinder is pi r squared h, and it took three of these, so this is 1/3 the volume. So the last thing I want to talk about in 12.5 is the cross section. So when we did 12.4 and we talked about prisms, we knew that the area of a cross section times the height gave us the volume. Well, as you can see from our two images here, unlike the cross section of a prism or a cylinder, a cross section of a pyramid or a cone is not congruent to the base. So you can see this cross section is a lot smaller than the base for the cone, and same for the pyramid. However, these cross sections are parallel to the base and they are similar to each other. So what ends up happening is you get this theorem. In a pyramid or a cone, the ratio of the area of a cross section to the area of its base is equal to the square of the ratio of the figure's respective distances from the vertex. That's a mouthful. But this actually probably looks very similar to a formula that you use in previous weeks. So if you remember, you did the similar figure theorem where you would compare the areas of two figures. So if you can recall, you know that the area of one figure to the area of the other is equal to the side of the one divided by the side of the other squared. So these two formulas actually look very familiar to each other. And if you remember when we did the frustum problem in class, what ended up happening is you actually had similar triangles or similar figures. So if I manipulate this a little bit, I can show you how there's actually from here to here, right? There's your two triangles. And we said that the triangle up above to the triangle, the whole triangle, when we did the frustum problem, they were similar. So what ends up happening is you get this ratio. So the area of the cross section over the area of the base is proportional as the height from the vertex. So height from the vertex for the top piece is k, height for the other one is h, and then you square that. So that's actually where you take all the pieces that you've learned so far and you put them together to get this formula. So now let's do some practice problems with volume of pyramids and cones. So number 1 says, if the height of a pyramid is 21 and the pyramid's base is an equilateral triangle with sides measuring 8, find the volume of the pyramid. So the first thing I need to do is, in order to find the volume of a pyramid, which is 1/3 base times height, I need to find the area of the base. So since it's an equilateral triangle, I use my area of an equilateral triangle formula, side squared √3/4, and I plugged in 8 for the side length. And that gave me a base area of 16√3. Now I'm able to plug into my formula, the base being 16√3, the height being 21, and when I multiply all that together, I'll get 112√3. Units cubed still, because we're talking about volume. So that is the volume of a pyramid. Now let's see if we could find the volume of a cone with a base radius of 6 and a slant height of 10. So the formula for the volume of a cone, we said, is 1/3 pi r squared h, 1/3 of a cylinder. And so in order to fill in the formula, the only thing we're missing is our height. So what ends up happening is, since we have the slant height and the radius, we're able to find the height of the cone using the Pythagorean theorem. Or again, if you know your triples, it's going to be a 3, 4, 5 in disguise. So the height is going to be 8. And now I can plug into my formula. So 1/3 pi r squared times my height, which is now 8. And when I multiply all that together, I'm going to get 96 pi. Again, units cubed. So the last video that you're going to watch is going to focus on 12.6, which is going to be the volume of spheres.